Thank you, and thanks to Morgan, Andrea, and Martino as well to give this session some momentum, and I hope I won't repeat too many things in my talk. I'd like to introduce you to rosc, which is a new client library that we're working on. It's extremely lightweight, portable, and it tackles the challenges of rosc in industrial and product development use, or it at least tries to do that. So I need to start by telling you a bit about the background of this development. If you ever build a complete robot from scratch, you know about this situation here. You need to put a big effort into establishing the infrastructure. You need to start developing software. Mostly you end up with a couple of PCs running various operating systems, automation industry components, and a bunch of microcontroller and FPGA boards that you probably even need to build yourself. So there are a couple of locations to develop for, probably using a range of development environments, but in the end everything needs to work together properly. Which is why we think in robotics, any other application that uses a multitude of sensors and actuators, we need to go towards distributed synchronized computing and control, and where efficient yet powerful nodes carry out a connected system's behavior and can transparently develop software that still runs across all of the system. So, which is why we developed an awesome technology and modular hardware software platform, which we call DINARC. It aims to take all the pain out of systems engineering and lets you focus on your actual application. But I don't want to advertise too much here, so let's see what it has to do with rosc. The system architecture that is supported by today's rosc is like that you have this one PC that runs rosc, and then a couple of distributed devices that you whether connect through something like USB, if it's a camera, or a Kinect, or when it comes to motor, mostly a field bus to which you interface through a rosc node that could be referred to as a proxy also. Like rosc serial, for example, or your custom design, like when using EtherCAT, you usually have an EtherCAT master wrapped into a rosc node. This is not good because while you close position control loops over the field buses, there is a limit of somewhere around 1 kilohertz for up to 10 axes, even when we're using high-speed standards like EtherCAT, for example. It's safety critical because mostly a single PC is in the loop, and as motion control is a real-time domain, it fights against the other stuff running on your PC, at least on the same machine. And this reduces quality of motion control, sometimes interruptions, and you have less resources for higher intelligence, like your perception, SLAM, whatever, making decisions. So now if we could allocate motion control as well as sensor data pre-processing to the distributed nodes, this would be awesome, we thought. And the problem is that field bus devices usually are no full-fledged PCs where you can run any software, and which is why we need a small client library for small embedded devices. And using such a client library, as you heard, micro-rosc node or rosc, using this, it becomes even more possible to distribute motion control and make it interact with perception at a low level, enabling you to implement things like reflexes without needing a PC at all. And to give an example, I guess you know about omnidirectional bases using mecanum wheels, like the KUKA U-Bot has it, for example. And classically, position control is carried out by the PC using a model dealing with the mecanum wheels and odometry. By setting speed and reading positions of the 4 wheels, which needs to happen a lot of times per second to be precise. Now, if we move this intelligence to the distributed motor controllers, we don't need to close the loop on the PC anymore. An abstract command a few times per second is enough, just once if it's enough for your application. And of course, in this situation, the local control loops on the devices can be closed much faster, like up to 10 kilohertz for position control, depending on what you do. For impedance control, of course, the computational capacity is the limit. And to send such abstract commands, rosc would be perfect. Of course, it's the same story for manipulators. I only took the example this mobile base. All right, so we want to bring ROS to embedded devices, but what is an embedded device? Morgan already did some definition on this, but within the special interest group embedded, and especially during ROS for Products workshop in February, we came up with kind of a classification. And we have kind of an embedded class, which refers to the Cortex-A or also an Intel Atom processor, where we have the challenge of bringing standard ROS onto it, which is also the effort of ROS on ARM, and but still use the same type of ROS that we already have. And the challenge for the small embedded device is, of course, to get this new type of client library that enables you to run the same middleware on those devices. And both are also application domains, kind of, where we use the small embedded devices mostly for control and data acquisition applications, while the big embedded class, or big embedded also, and a big x86 could be also an embedded, but let's say the Cortex-A class for things like perception and intelligence. Whatever intelligence is, in this case, can be many things. So rosc is an implementation of the ROS middleware. Currently, this means master communication via XML RPC and node-to-node communication via TCP ROS. It's lightweight. That means by requirement smaller than 32 kilobyte on XMOS chips. It has no dependencies at all and is written in pure C, the language that is supported mostly by any platform. Our reference platform is XMOS, and you probably never heard of that. But it's an amazing piece of hardware, multi-core, up to 32 cores. Real-time hardware support on a hardware level, and it's clocked up to 700 megahertz per chip. So it delivers FPGA performance, but also has FPGA-like memory resources, only 64K per tile. And because everything needs to happen fast in this architecture, unlike other micros, and XMOS also runs programs from RAM instead from Flash. So we need to use those 46K for program as well as data. And yeah, so if you listened to the MicroROS Node talk before, you probably wonder how is rosc different. Both developer teams a couple of weeks ago did as well, and this is why we hooked up and also synced up to see what are we doing different and where are we going to. And first of all, MicroROS is an academic project, and rosc is a commercial open source project. And MicroROS is available for use today. There are working demos available, and rosc is still under development. But on a technical base, there are three main differences. rosc has tight down memory constraints, mostly because it shall run on bare metal systems, and the issue I told you before, where MicroROS until now relies on an OS. The bare metal reference that we use, and that also sets our requirements, and the fact that we want to support more than just Ethernet communication in the long term, leads rosc to have a modular transport layer concept where MicroROS uses yet the OS infrastructure with LWIP. This modularity of rosc especially tackles portability. rosc has a package concept that lets you adapt it to any platform. Main contains the client library itself. Now, to support various OSs, there are support packages that, for example, lets you interface to the Ethernet driver of your Linux. On bare metal systems, the way in which you interface to an Ethernet device is totally different from how you interface a Wi-Fi module, for example. So we also need to support each of these as well. The same applies to the various platforms. They need to be supported as there is no OS to care for that. Now, of course, you, in the end, add your probably already ROS-compatible code, which is also why we'll add a C++ wrapper to it, so that you could potentially use the same code that you had, if it's fitting the platform, of course. Now you take your probably already ROS streamlined code and put it together with the packages you need for your platform, and receive an executable for an OS or a flashable, bootable image for your micro. That's it, and our goal is that it shall just work for you as standard ROS does. But there is some pain in developing this. I guess you already heard of XML RPC. Just before in Andrea's talk, there was already a short screenshot of this. Yeah, so this is XML RPC. You can imagine the challenge to keep a multitude of these messages in a few bytes RAM and running it fast. No further comment. So where we are currently, we have an acceptable fast XML RPC streaming parser, which is more or less the biggest part of the story. It is almost fully validating, but does not support encoding like gzip, and you need to set a limit for the tag depth that you want to be able to parse. Of course, it has a message generator as well, port interface handling, which is naturally limited on bare metal systems, like for example Wi-Fi modules where you have up to 8 sockets mostly, and support for TCP ROS transport, so everything you need to communicate with the master and other nodes. But what is more interesting than these essential features is what is about to come in the future. And jumping back to this diagram here, where I said you could implement reflexes, for example, it's easy to see that real-time capability would be very useful here, where those reflexes being messaged. Now, our long-term aim is well to make all software running on the distributed nodes communicating with ROS middleware. That means even locally on one microcontroller. So here we need real-time even more. And this is a summary of the requirements that we came up while talking to ROS Industrial participants and also the participants at the ROS for Products workshop in Mountain View. And some of these we want to address in the long term with RosC, which is especially the real-time capabilities. We want to play around with replacing XML RPC by something else. Want to evaluate master-free concepts and want to make it transport layer independent, because you not always have Ethernet at your micro or distributed node. You also want to use CAN bus, EtherCAT, and probably even a serial link. And yeah, so I'd like to, in addition to that, show you a little bit what we currently think could lead to a real-time capable ROS. And if we look at today's ROS, there are main two issues with making it real-time capable. One is that IP transport is not really real-time naturally, and the client implementations which are there currently do not support RTOS mechanisms in a good fashion, like, for example, the scheduling and prioritization of processes. And this is our current state of how we see we could realize real-time capable ROS, at least within RosC. So you could also look at RosC as being an experiment lab for the aspects, or some of the aspects, that could come into ROS 2.0. We want to add, besides the TCP ROS, UDP ROS transports, things like COE ROS, which would be can open over EtherCAT, CAN ROS, and local ROS, which means with no network communication at all, to make two nodes on the same machine communicating with each other. And once you have master communication taking place over kind of a broadcast channel instead of having a master. And yeah, so, but why are we focusing on those transport layers? This is because we think transport is one of three aspects that ROS needs to change, or we need to change with ROS to make it real-time capable, and to enable those real-time capable transport layers to work properly. We also need to separate the master communication, which is mostly not real-time. It also does not need to be real-time, from the process communication handling, process message handling. And this is also why we need to implement, or do implement, rosc in a multi-threading manner. That's essentially it. This is a lot of work, and this is why I invite you all to join the project. Right now it only has one developer. He's sitting here, and what is this? And he is also willing to answer your questions if you have more deeper technical questions. And I'd like to also state an invitation if you're seriously interested in the stuff that is discussed in ROS Industrial and ROS for Products forums. We're going to give kind of a chill-out event at Columbus right over the street. And yeah, there will be free beer. So if you want to join the discussions and the plans for next year, come over and have us. Thank you.